confused at the moment. Who was at the Wildlife Society meeting last Thursday? Remember Sierra talking about models. She got offered a graduate assistantship at a school that is a modeling school. And she's like, I don't know if you guys know what models are, but it's all computer work, right? To this point, for the most part, and unless just a little bit here and there, you guys really haven't been exposed much to the concept of wildlife modeling, have you? Have you heard of the idea or the concept of models? Do you have much of a sense, do you feel like you have much of a sense of what that means, what it is?
Are we talking like models that we did in like 240, or what class was
Like,
that?
is it like animal ecology, like
yeah,
models like that?
There are models in there, like models, models of, there's home range models, there's models of, that allow you to estimate population sizes, so there's mathematical models, that we can use. Those are examples of models. But I'm going to talk a little bit more about what models are. She said they're all on computers, and largely it involves computer work. But I'm going to talk more about that. Some schools, that's a lot of their focus is modeling. Virginia Tech is well known in the southeastern United States. It's an excellent wildlife modeling. But let's talk a little bit about models. And I've got I think I have like 8 or 9 slides on this lecture, and then I'm going to give you, your first homework assignment, which was supposed to come in, right after you turned in the management plan. So for those of you that haven't completed the management plan, I tell you what I might be willing to do is I might be willing to make this homework assignment. I'll give you 2 weeks for this, although you should probably be able to get it done pretty quickly. It'll take you a few hours one day, but still, I know you're working hard. But and then once I give you that homework assignment, if we have time, keep it in mind. You guys might not know this, but this is only a 50-minute class, not a 1 hour and 15-minute class, right? I'll go on to the next part, which is habitat associations, which is a more specific type of wildlife habitat model. So the purpose of models is to come to some greater understanding of wildlife species or ecosystem or relationship between wildlife and their habitat. To understand perhaps what are the things that's affecting the species distribution or abundance. Why are there pheasants in Illinois but not Tennessee? Why are there ruffed grouse in the Appalachians but not the Cumberland Plateau? Why does this animal eat leaves from this tree but not that tree, etc. So better understand what is it that animals are keying in on? What is it that's important to different species or sexes or ages? Models can be used in some cases, very often they're misused here, but they can be used to predict future distribution or abundance. If we have this abundance of this species, and we understand the habitat, and we know that if we improve the habitat in that way, it's likely to result in a 25% increase in density, then if we start implementing controlled burns, or if we thin out this or allow hard mass producers to increase or whatever, then we can expect this sort of a response from wildlife. That predictive ability of models, I say it's often misused. People will take a model, and I'm going to talk about this in a minute, and do something called hindcasting. What happened? We did this and we saw this happen. And then they'll take that information, hindcasting, and they'll forecast with it. Since it happened that way in the past, if we do it over here, or if we do more of it, we can expect that to continue to happen or to happen again. And that might not always be the case, because maybe we implemented controlled burning and the animals doubled in population density because it was a locust year, and there was a tremendous food supply in locusts, and they didn't increase because of the burn, they increased because of something that we weren't even looking at. So we have to be really careful about using models to forecast. Make sense? Okay.
we can use models to figure out, what are we missing? Where do we have weaknesses in our understanding of species-habitat relationships? And we can use them for generating hypotheses. We saw this happen. Why might it have happened? Well, maybe it happened because of prescribed burning. Maybe they increased because it was a locust year. Maybe it was, now let's do some studies and look at the effects of each one of these and see which one had an effect. So we can do a lot with models. So a lot of people say, oh, that's computer work. I don't like that. I just like field work. Well, models often work with field work to allow us to come to a better understanding of wildlife. So we might not always love them, but they can be very valuable. You can categorize models in a million ways, but one pretty simple way of doing it, and you could see this on the next test, is these 4 forms of models. And you can also think of these as more and more specific, and you could think of them as 4 steps in a model building process. So the most basic model, you could say, is just a concept. It's an idea that squirrels eat nuts, that squirrels live in the woods, that deer spend part of their time in the woods and part of their time in early successional habitat. Okay. Oh yeah, and I have not put this on Canvas yet, but I can. I will. Okay. All right. So if I go too fast, no worries. So that's the conceptual model. The next comes the diagrammatic model, where we diagram it. We draw a picture of that idea. I cannot tell you how many hours and how many pitchers of beer I have spent and drunk talking with other wildlife biologists and graduate students and major professors in a pizza place with a napkin and a crayon, right? That if we did this and we're just drawing out our ideas, and there's a million ways that can be done. But it doesn't involve statistics, it doesn't involve math yet, it doesn't involve necessarily or usually numbers yet, but it's making that idea more concrete, okay? And there's a million ways that can be done. So the next is the mathematical model, where there are numbers to it. So some of you guys have been in a class or two where we did the Lincoln-Peterson population estimator, where we estimate population sizes by capturing a bunch of animals and putting marks on them and letting them go, and then catching a bunch more animals and counting how many there are and counting how many have marks. And we use this Lincoln-Peterson equation, M1 or N1, the number you captured the first time, times N2, the number you captured the second time, divided by M2, the number that were marked in that second capture, and that gives you a population estimate. Okay, so that's a mathematical model. We're not running any inferential statistics. We're not looking at is there some reason why this population increased faster than this population? That would come next. So the computational model is where we go into those inferential statistics. So that's 4 stages of the model building process, or 4 forms of models. Good? Okay. Well, there's a lot there, right? We can also think of models as falling into these different categories. And what we have here, I have these grouped into alternatives, okay? So where you have a group, it generally can't be all of those things. It's one or the other, or one of the 3. So first, a model can be either theoretical or empirical. A theoretical model is just based on speculation. An empirical model is based on real data that you go out and collect, okay? A theoretical, a conceptual model is theoretical. I'll show you a flow chart in a few minutes. I'll just go through these. So empirical is based on real live data that you collect. A model can be descriptive or statistical or mathematical. Descriptive is just words or drawings, outlines. So that conceptual or diagrammatic model would be descriptive. Statistical, you test a hypothesis. You use inferential statistics to test, is there a relationship or a difference or not, okay? Mathematical is just using numbers to do, like I said, that Lincoln-Peterson, where you just use a mathematical equation to get to an answer. We're not doing a statistical test to determine if there's any relationship or differences. We're just using these numbers to get to an answer, okay? Some models are very simple and they deal with one variable, right? That is called a univariate model. Uni is one variate is variable. Bivariate, bi is two variables, so two variables, or multivariate greater than two. So how many variables are we looking at? When I studied winter ecology of blue grouse in northeastern Oregon, I would put radios on these birds and I would follow them around, and I would look at, okay, first of all, what species of tree are they in the wintertime, okay? And if that's all I looked at, that would be a univariate model, okay? They spent some of their time in Douglas fir and some of their time in ponderosa pine. But I also looked at the diameter of the tree that they were in, okay? So that makes that, any modeling I did then, a bivariate model. I also looked at some other things too, like height of the tree, elevation of the tree, age of the tree, or the other birds, how far are we from water, how far are we from roads, and many other things. So the modeling that I was doing was multivariate regression models. Okay. Models that are run in such a way that you plug in one number and see how it changes the model is called a deterministic model. And based on how it changes, if we change the frequency of our prescribed fires from once every other year to once every third year, how does this change the outcome? Okay, that's a deterministic model. Okay, but if we change lots of things, there's any number of ways. So we could change the prescribed burn frequency from 2 years to 3. We could change the way we harvest timber. We could change any number of other things. Well, there's up to an infinite number of possible answers then. And in that case, that's called a stochastic model. And what we often do with stochastic modeling is when we have a whole lot of variables that we're looking at, we'll have the computer run a simulation and plug in, or run a series of simulations and just plug in a random variable. So you tell it, okay, randomly choose a number between this and this to represent how often we do a prescribed burn, between every 2 years and every 10 years. Randomly choose a number between this and this to say how big our clear cuts are going to be. Randomly choose a number between this and this, and then do it. Now do it again. Now do it again. Now do it again. Now do it a million more times. When I was in graduate school, we would do these stochastic models, and you get it all set at the end of the workday, and you'd hit go, and you'd ask it to run the model 100 times, and you'd come back the next day and hope that it was done. Today, our computers are so much stronger that you can tell it run it 1,000,000 times, and it might take it a few seconds or even a minute or two. So our computers are so strong today that stochastic models are a lot more useful. And from those, we can build inference. So some of you have heard me in other classes talk about population viability analysis. That's an analysis using stochastic models to say, okay, based on all these things, if you do this and this and this and this, we can say that there is a 62% chance that you're still going to have a viable population of at least this many animals within 100 years. Okay, so those are complex models that accommodate lots of variables to give you a likelihood based on just running simulations almost countless times. Okay, models can be hindcasting and forecasting, which I talked about a second ago. Hindcasting is fitting data to what you saw. This is what we did. This is what we found out. Our best understanding is this is why that happened. Forecasting then is taking that and saying, were we right? Are we reading that correctly? If so, let's use that, our interpretation, and see if that happens in the future. If this happened this way here, so let's do it here and see if the same outcome occurs. And if it does, we've got a model with predictive power. That's valuable. Right? And that's what we all would like to have. You use what we've learned from the past to anticipate if we do this management practice to the habitat in the future, we should expect this response, right? And we in the in mass media, we make it sound like, oh yeah, we need more quail, so we just need to shoot all the coyotes. Or we need more quail, we need to plant native warm season grass and do a prescribed burn every 3 years. Boom, and we'll have more quail. Well, that's hoping that our conceptual models of the past are going to work in the future, and very often it may or may not. Models can be analytic or simulation, where we just look at each part, or a simulation where we imitate things of the future. So I won't ask you for much more complexity than what I've given you right here, but you could see these on the next test. Okay. All right. So this takes all what I've just talked about and puts it into, with regard to wildlife habitat relationship models, how they can fall. Okay. So we can break them down by the source of the model. Is it based on real life data that you collected in the field? Or is it just theoretical stuff? It's not real live data, okay? The form of the model, it can be descriptive. Deer spend part of their time in the woods and part of the time in the field. That's just a case study. Or they can be statistical, okay? And then theoretical models can be either descriptive or mathematical. It can't be statistical because we haven't gathered any data to run an analysis on. So we just use hypothetical numbers, okay? The complexity of the model can be simple, univariate, or even bivariate, or can have a lot of variables. Theoretical model can be one variable that you're looking at, deterministic versus stochastic, a lot of variables that can vary. And then the purpose of the model can be hindcasting, and I'll talk more about habitat selection models hopefully in a bit if I have time, or forecasting, which we often try to do maybe when we shouldn't, but that's very valuable if we can. And then theoretical models can be analytical models where we are often pretty basic. We're looking at changing one variable and how does that change things, or a few variables, or a simulation like a population viability analysis that I just talked about, okay? So I'm going to give you an example, bless you, in a minute, of a habitat suitability index model. And you're going to do a homework assignment using this, okay? So this is a theoretical model that uses mathematics. It's a deterministic model, not a stochastic model. And it'll give you a numerical value that serves as an index, habitat suitability IS index. And I'll talk about indices in a minute, okay? So, if we have time, we'll also get to a habitat selection model, which is some of you have done if you've taken the wildlife research class. You've done it in the form of a chi-square analysis, and I'll show you that again. All right. So next, we're going to learn each of these models. I'm just joking. We're not going to learn any of these models. So sorry. But these are just examples of the wide variety and applicability of models. Just read through some of these. Species responsive vegetation structure, models of vegetation structure, stand growth and yield, succession models, single species, life history, habitat preference, optimal foraging, correlation, multivariate statistical models, HSI models, habitat capability class models, habitat evaluation procedures, Bayesian and pattern recognition, population trend and viability analysis, indicator species models, multiple species, species habitat matrices, Gildan life form, community structure and simulation, hierarchy, semantic, landscapes, vegetation disturbance, fragmentation models, FragStat was a great program, cumulative effects, insular biogeography, monitoring species and habitats, adaptive resource management, knowledge-based and decision aids, decision support models, expert systems. There are all sorts of models out there. And when I put them together like this, it just makes you go, bleh. I don't want anything to do with any of it. But, when you're working intensively with a species and its relationship with its habitat and trying to figure out how to best manipulate habitat to favor that species and how to figure out how to do that, very often in graduate school and in advanced research, we find some of these models very useful. So, you don't need to know any of this right here, okay? Okay, so the example I'm going to give you, like I just said a moment ago, is an HSI model, a Habitat Suitability Index. Don't get it backwards and write HIS. That means his, it belongs to him, and that's different. Okay, so what this model is, it takes the geometric mean, usually of 3 environmental variables that research has shown us what we believe to have the greatest impact on the presence, distribution, or abundance of species. Now, the basic form of the model is here, but it often can vary. And as a matter of fact, what you're going to be using on your homework assignment, the model is going to vary from this just a little bit, but you should be able to figure it out easily enough. The basic model is this, okay? Variable 1 of those 3 environmental variables times variable 2 times variable 3 to the 1/3 power gives you an HSI value. And that value is going to be a number somewhere between 0 and 1, okay? 0 means it's shit habitat for that species. 1 means it's perfect. 0.5 means it's about half good for that species, okay? Simple as that. Now, each of those 3 variables is going to be presented also as a decimal, somewhere between 0 and 1. Okay? So if perfect conditions for gray squirrels means that you've got a forest stand made up of 80% hard mass producing trees that are at least 40 years old, and you have at least 50% canopy closure, and anything older and bigger than that is perfect, and you have that, then variable 1 would be 1. If you don't, it would be less. And I'm going to show you this graphically in a minute. It's going to make it more clear, okay? Each variable and the resulting value is somewhere between 0 and 1. The final value, the response of the species, the combination of those 3 variables, 0 is like, okay, I already said that, just said that, okay, good. Good so far? You okay?
Yeah.
Okay, all right. I'm going to show you this graphically, and it's going to help you, okay? I'm going to give you an example, okay? This is an example of the yellow warbler, all right? So the first variable that they say is the percentage of deciduous shrub crown cover. So first of all, deciduous means non-evergreen. Shrub, what's a shrub?
Small woody plant.
Yeah, it's first of all, it's a plant. Second of all, it's a woody plant. And third of all, it's smaller than a tree, right? How big does that have to be? I mean, when does it become a tree? And when does a pond become a lake? It's kind of subjective. Some people say 3 or 4 or 5 meters, but whatever. So percentage of the crown cover of those shrubs. So crown cover of trees, we talked about canopy cover, right? Do you have 100% canopy cover of the canopy in a forest? So this is the shrubs. You have 100% or 50% or less. And we're actually going to do some vegetation monitoring later that looks at canopy cover. So what this shows on the right is the percentage of deciduous shrub crown cover. That's the x-axis. The y-axis is the suitability value. So what this is saying, if you have no deciduous shrub canopy cover, this variable 1 is going to be 0. If you have 25%, you go up and over. So that variable 1 looks like just below 0.4 maybe. Does that look about right? You just go up to that line and then across. If you have 50%, what's that going to be? Around 60.65 or so. You know, you can use a ruler to figure it out. If you have 75, well, when you get to, there's 50, there's 55, there's 60. When you get to 60% deciduous shrub crown cover, the variable 1 becomes 1. Perfect. All the way up to 60, 65, 70, 75, 80, up to 80%. So from 60% to 80%, deciduous shrub crown cover is perfect. More than 80%, it starts going down again. So that by the time you get to 100%, it's down to 60%, to a 0.6 for that mean. Okay? So average height of deciduous shrubs goes from 0 meters up to 2 meters. So it just gets better and better the taller the shrubs are, okay? And then percentage of the deciduous shrub canopy comprised of hydrophytic shrubs. What does that mean, hydrophytic? Water-liking shrubs, such as buttonbush, right? Versus a non-hydrophytic shrub like American beautyberry, okay? So the more the better. All right, so do I have an example here? No, I don't. So let me give you an example, okay? Let's say that you go out to Gooch WMA and you collect data, and then you find on average across the WMA that the percentage of deciduous shrub crown cover is let's say 30%. You can just eyeball it and look at what you think that the V1 suitability index value would be and write that down if you need to, because I'm going to have you do the math here in a second. So 30% for V1. Let's say the average height of deciduous shrub canopy is we'll keep it simple, is 1 meter. 1 meter. And let's say the percentage of deciduous shrub canopy composed of hydrophytic shrubs is 75%. All right. Grab your calculator, do your math.
What did you say about this one?
Which one?
The V1.
They're all V's. Which V? Oh, V1. Okay. The V1. V1, I said 30%. 30% right there. Now your numbers might differ a little because you're having to eyeball that HSI value for each one, right? So it's V1 times V2 times V3 to the 1/3 power. And if you're not sure how to do the 1/3 power, you look for the Y to the X button and then put 0.33333. Who's got it?
0.58.
Huh?
0.58.
You got 0.58?
Yeah, they're doing
0.56.
my codes, so.
You got 0.56? Anybody else have something yet? Garrett, you got anything yet?
No, I'm confused.
How can I help you?
So how are we determining what V1, V2, and V3 is?
So when I told you that percentage of deciduous shrub crown cover is 30%,
Oh,
you imagine a line that goes up until you get to this line, and then you go across and look at what the numerical value would be. And that would be your HSI value for V1.
okay. I missed the
Okay.
30%.
So you take that number times that number times that number to the 1/3 power. How's it going, Gabby?
I'm trying to eyeball it.
It's okay. This is not a test. Do the best you can. You got it, Caitlin? Oh yeah, you said you got one.
0.56?
Yeah. Audrey, how's it coming?
Calculating it right now.
Excellent.
If you turn your phone sideways, you'll be able to get more options.
Or you could just pull out your graphic calculator. I always have mine.
Yeah, when somebody showed me that turn your phone sideways thing, I almost
changes
passed out.
it.
It was so amazing. Yeah.
Tell you how old we are.
Yeah. Yeah. Did you not know that?
I did.
Is that not amazing or what?
Didn't have a clue.
Yeah.
I'm on my days.
I got 4.
0.54?
Yeah.
That's okay, like I said, you're just eyeballing this, you know,
I don't
here,
have
so,
very good
yes.
eyes.
And I'm gonna have you eyeballing it for the assignment too, and that's okay, so your numbers might vary just a little
So
bit.
if I go roll 0.5 something
Yeah.
is good.
You hope so, yeah.
Hope
yeah.
so.
Have you got it yet?
Yeah, I was on this little calculator.
Okay.
I regret that.
No.
Okay.
Okay.
What did you
How about it, Garrett, you got it?
Yeah, I got 0.58.
0.58?
do? 370?
Did you cheat?
No.
Did you look at her stuff?
No, I
Probably.
got it.
Okay, okay.
Probably.
I
You probably
Okay.
cheated.
just got higher, it looks like a 0.8.
I swear not.
Dude,
Not this bad.
Yeah, better, yeah,
0.54.
0.54, okay, okay.
My eyeball wasn't.
That's all right, that's all right.
Saying, I don't have good.
You understand the idea, though.
Yeah.
That's, it's not, yeah, that's the important part to me. Jeremy, did you get it?
it'll come.
5.4.
5.4?
Yeah.
Okay.
But it's
It was
coming.
like, I don't know what's it.
Yeah, see? I'm sorry, I'm a loser. I'm an Android.
No.
No, I've got it.
I've been
Androids are
told I'm
valid. You're so valid.
Whoever tells you that is a loser, yeah,
Oh.
come on, there's no,
What are they? Said that.
we're all winners and all
Alright,
losers.
nice.
I don't think we're all losers.
What the heck?
Well,
There's-
look at,
no,
we
there's
all die,
definitely guys
we all
that
eventually
suck.
die, you know, so,
I think it was 5, 6.
yes, so, I mean, no, well, we lose something, but the point is, it's not useful or
Yeah.
valuable to even think that
Some
way.
people got lose. Not everyone
True.
can win.
It's philosophical.
Listen, my
So
last.
we-
You
the
would say that,
Olympics.
Garrett.
We were at the demo.
Liv, did you get it?
Yeah, 5.56.
0.56, okay, good.
That's simple.
So you guys all understand how it
Someone's
basically
gotta be
works,
better.
okay? So, you know, with that information, if you were the WMA manager for this WMA and they said, we want you to manage for yellow warblers, what might you do?
Increase the shrub crown cover.
Why do that?
It's low.
Hmm?
It's low.
We want it to be 1.
When you say it's low, you mean it's relative to those three, that's the lowest of those three variables?
Yeah, probably.
Right, okay. So what could you do to increase the hydrophytic deciduous shrub crown cover?
Plant more. Hydrophytic.
We're not even the hydrophytic yet, actually.
Oh,
Yeah.
Within the deciduous shrub crown cover.
Why might you have low shrub crown cover?
Too many trees?
Maybe there's too many trees. So you plant more and they're all gonna die if you have too many trees. So what could you do then?
Inoculate or single tree or group tree selections?
Yeah, so, why do we have not as many shrubs as we might? And if it's because there's too much overhead canopy cover, knock some of that back. Exactly, right. Yeah, makes sense? Good, okay. So do this, not now. Now, this is a scenario, I hope it'll be kind of fun. It's for the pileated woodpecker. And if you go to our course Canvas site, on the main page, the top module, I've got the HSI for the pileated woodpecker. Now the HSI, the HSIs, that they don't use them so much today, although I think they're still cool. But they were really big in the 1980s, okay? And they came in the form of a report that's several pages long. It includes like life history information on the species and a bunch of stuff that you don't really need. You don't have to read the whole report, okay? But you're gonna get to a point, if I remember right, for the pileated woodpecker, it might say, use this model for the western United States and this model for the eastern United States. And or it might say, this is the upland and this is the bottomland. And if you're in a bottomland, then you use the bottomland model for the eastern United States, okay? And sometimes the models look a little bit different. They might look something like variable 1 times variable 2 to the 1/2 power plus variable 3 or something else, okay? But the model, it'll tell you, and it'll tell you what the report will tell you. And you'll just follow that model and use this concept that we've used here to come up with an HSI value. And that value is gonna be, if you've done it right, somewhere between 0 and 1. And
then you'll do the rest of it. I'm gonna ask for a one-page report on, doing kind of what we just did, but more, with more depth. Where are we weak, and what do we do to get stronger in that area, to increase that HSI value? Good?
So you want us to type out our answers?
Yes, you're in college.
Just wondering, is a piece of paper, want me to write on it? or
Yeah,
type
Grova.
it?
Type it out. Type it out, yeah.
You already given us 2 weeks to do this, right?
I'll give you 2 weeks to do it, okay? All right, so whatever is Monday, 2 weeks from today. Write that down. Or you can type it
November.
if you'd rather.
November
okay,
what?
So what do you want us to do?
So
Say that again.
November
I
6th.
didn't type that.
When is it due? November 6th? November 6th.
November 6th, okay, but what do you want out of it? What do
I want you to do exactly what it tells you to do, right there.
Just type it out.
Yeah,
Type your
you're
answers.
You're about to get your jaw.
Did I miss your question?
You said what you wanted, like, type on paper a minute ago. So
I want you to type on paper what it tells you to type.
Okay, I'll do that.
Yeah.
Are we turning it on Canvas? Does it say that?
Yeah.
Y'all are so full of, would you rather do it on Canvas or hard copy?
Canvas.
Canvas.
Canvas. Okay, Canvas is, do you know how to do this on Canvas?
Same as homework assignments?
Yeah.
Yep.
Yeah, okay. Turn it in on Canvas.
Why did you sigh when I asked that? That was
Sorry.
a good question.
No, it was a good question, because I hate Canvas. I hate it.
It
This
gives
means-
us more
We
time to do it.
Sure. This means that I've got to create
How
a.
much work is it for
Technology?
you, Reed?
How about all those reading assignments we've submitted?
It's only Monday.
There's the amount of time it takes, there's the amount of mental energy that takes.
Old Will's